Another day, another DSA problem. So let's look at 2812, find the safest path in a grid. This was actually the daily problem from a few days ago, but I couldn't make a video, so I'm just making it today. Yeah, so the problem here is, obviously the problem statements are a little confusing if we just read it out here. So let me just go ahead and explain it, and then we can proceed from there. Okay, so what the problem says is that we are given an n into n grid, and each cell in this grid either has a 0 or a 1. So a 0 represents an empty cell, and a 1 represents a thief. So they've given a few definitions in the problem over here. So I have just written them out because it's going to get confusing later. So let's just look at these. So what is a safeness score? A safeness score is present per cell. And the safeness score of a cell is defined as the distance to the nearest thief. Okay. We will see this in more detail over here. Let's just check this. Okay, so the safeness score, as I mentioned, distance to the nearest thief. Let's take an example of the cell which is at 1, 0. So that's this cell over here. Now, let's see what the safeness score to this for this cell is. Now there's a thief which is 2 steps away from it. So it could be 2, but because we are talking about the nearest thief, I see that the nearest thief is over here, which is at a distance of 1. So the safeness score of this is 1. Now let's take another example. Let's talk about this cell, which is at 2, 3. Now, so the distance to the nearest thief, they've actually asked for Manhattan distance, which is basically like if I construct layers like this, and I can go like, where do I go next? Yeah. So if I start considering those layers, which is the nearest thief, right? So I went 1 layer and then I went to the second layer. So the safeness score of this, the distance from the nearest thief, is 2. Okay. So what do I mean when I say this, these layers, right? So this basically translates to the number of BFS layers to the nearest, to the nearest thief. Okay. So yeah, it's much more easier since we kind of established that it's a BFS and we need to look at layers. Now let's look at the next definition that we have, which is the safeness factor. So a safeness factor is present for a path. Now, what does that mean? So it's the minimum safeness score among all the cells in that path. Let's look at that in more detail. Okay, so they have defined that a path is basically like from where do we go, from 0, 0 to n-1 to n-1. So it's from here to here, right? Now let's look at this path. Okay. So if I consider this path, as we see, it's the minimum safeness score along that path. So if I see the minimum along this path is 0, right? So from this path, I get an answer of, I get an answer of 0 if I consider from here to here. Now let's consider this path, okay? So even in this path, I see that 0 is the minimum. So I get 0 over here. Now, what the question actually says is we want to maximize the minimum safeness score, right? So that is the goal. I didn't get to that, but yeah. So the goal of this whole problem is we want to find the path with the maximum safeness score, all right? So we want to maximize the safeness score itself is the minimum of all the cells in that path, the safeness score of all those cells. So we want to maximize that. Now, in this case that I saw, actually, this became 0 and this became 0 as well. So both of them lead to 0, but we want to maximize that. So let's just say there was an example where this was something else. Okay, this was not 0. Let's just, for example, take this as 2 and this is 2. So this path would have given me, the minimum of this path would have been 1. So it would have been better to take this and come here because this is a much safer path, right? If we look at the definition of what the safeness factor actually means. So the answer would have been 1. Okay, so that's the goal. Now let's see how we're going to solve this problem, right? So the first thing we're going to do is, because safeness scores are important to us, we are going to calculate and compute the safeness score of every single cell. And it's worth noting that every thief is obviously, it's close to it. It is itself, right? So the safeness score, which means the closeness to the closest thief, obviously the distance to the closest thief. So for every thief, the safeness score will be 0. That's worth noting. And why don't we do one thing? So let's consider, like, okay, let's consider this a thief, right? And then I look at all of the cells which are beside it. And I know this is at a distance of 1, this is at a distance of 1, and then another cell here would be at a distance of 2, and so on and so forth. So why don't we actually push all the thief cells into a queue? And then from there, let's start doing like a BFS. Okay, if there's another thief, we'll do a BFS from there. So basically, we are going to do a multi-source BFS. So let's look at the algorithm for what we're going to do. It's multi-source BFS, right? So first, we're going to push all these thieves into a queue. And then let's do this. We're going to mark the thieves as 0. And then we're going to mark other cells as -1. So why is it 0? Basically, I am going to use this grid itself to store this safeness score. So as we saw, the safeness score of a thief is 0. And let's mark everything else as -1, because we can also use that as a visited sort of thing. If it's not -1, then we can update it. And then if it is if it's already a value which is greater than -1, it means we've already found the minimum of it, safeness score to it. So let's just do that. It sort of helps us in both ways. And then we're going to do a BFS outward, just like what I described here. And the first time a cell is visited, like I mentioned, we're going to check with this. It will obviously hold the value of the shortest distance to a thief, the closest thief, basically. Okay, so if we do this, let's see what the time complexity of this would be. It's going to be O of n squared. And why is that? Because in the worst case, all of our cells could have thieves. Then our queue would basically be everything, right? We would have n into n cells, so that's n squared. And we'd go on like popping from the queue every time. So yeah, that would be O of n squared. And if we look back at what the goal of the problem was, it was to maximize the safeness factor. And as we saw, the safeness factor was the minimum safeness score, in the path. So if we consider all the cells, which was the minimum safeness score amongst all those cells, so we want to find the path which has a minimum that is maximized, basically. Okay, so if you are a frequent solver of LeetCode and DSA problems, then you know that when it comes to something like maximize or minimize, we don't want to just generate all the paths. We want to look for something which is much more efficient, right? Generating all paths might be exponential. So let's make an observation here. We know that the minimum value of the safeness factor could basically be 0, right? Because wherever a thief is, it is 0. And the maximum safeness factor would be the maximum safeness score in the grid, right? You can obviously not have a value greater than this. So we have established that there is a range. We have a low and then we have a high, and we are 100% sure that our answer will lie between low and high. So why don't we perform a binary search on this answer, right? And if we do that, as we know, binary search would be n log n. That's not n log n. Yeah, so it's log n. Okay, so here's what we're going to do. For every candidate mid, obviously low plus high divided by 2, I'm going to go and check, can we find a path where every cell has a safeness score greater than that mid? If I do find a path like that, then it guarantees that the minimum of that path is mid. So I'm guaranteeing that the safeness factor of that path is mid, right? And then what I would do is I would take that as this may be the answer, but then I'm going to push it further, and then I'm going to increase low, and then I try to keep doing this as long as I can, and I'm going to try to maximize answer because that is the goal of the problem. So yeah, I talked about checking this, right? Can we find a path? So we're going to call a function like this is valid path, and we're going to pass in this minimum safety, which is basically our mid. And what does this function do? Check if a path exists, right? So this is going to be a BFS again. And from that path, from the starting cell, basically from 0, 0, I'm going to start, and then I'm going to look around it. And what I'm going to keep doing is anytime I find a cell which satisfies this condition, the cell has a value which is greater than or equal to mid. So that mid can be it can basically be our minimum safety. I'm going to take that path and I'm going to keep going. So basically, if I see that while continuing towards this BFS, if the destination cell is reachable, then it means answer is mid, possibly this is the final answer. And then I'm going to try for a greater value because the goal is to maximize, right? And let's say I was not able to reach the final destination point and comma n using these specific rules, let's say, by using this. If it's not possible, then I know that my value of mid is too large, and I'm going to try for a smaller value, and I'll basically do that by doing our high is equal to mid minus 1, and then I'll continue my continue my search for the optimal value of answer. Okay, now let's look at the time complexity for this. So as we saw, binary search was log n. I wrote it wrong here. It's log n. And then for each binary search, I'm going and I'm checking a function. So there's that function. Yeah, I'm going and calling this function, right? Is valid path. And is valid path is basically a BFS. And as we saw earlier, the time complexity for this BFS is O of n squared. So for every log n times of that binary search, I'm calling n squared, which is our BFS. So it's what? N squared log n. Yep. And then the space is obviously O of n squared. I think because we have a queue, right? And the queue could possibly go to n squared size. So yeah, that, and then we're just storing values in our existing grid already. Yeah, so that's basically the algorithm we're going to be using. It's a multi-source BFS, and I think we can just jump to the code. That is better for us to understand. All right, so the first thing I want to do is kind of hold like rows and columns over here. So that can be the length of the grid, and we're given that they're both the same value. So again, length of the grid. And then we wanted to do a BFS initially to get the safeness scores, right? So we will start, let's just write that here. Calculate safeness scores per cell. And we talked about how we started from the sources, right? So our sources will be, so it's going to be a Q, right? So since we are doing BFS, it's going to be a DQ. So let's do that. And then we want to fill this with the value of the thieves, right? So that will be stored, and then we'll do a BFS from there. So first, let's just write this. Let's collect thief locations, right? Yeah, so for R and range rows, for C and range columns. Okay, so I also talked about one thing. We're gonna mark the safeness score as we go, because we wanted our thieves to be 0, right? We'll just do that part over here. So we'll see if grid of r comma c is equal to 1, because that denotes a thief. Then I want to add that thief. So sources dot append r comma c, and I also want to update its safeness score. So grid of r comma c will now be equal to 0, because thieves are, I mean, obviously they're themselves, so their distance is 0. Or else, if it's not a thief, then I can go ahead and put that as -1. So we'll just use this later as sort of our visited just to check if we visited that or not. Okay, so the next step would be to do a BFS from multi-source BFS. Let's write that. So multi-source BFS from all the thieves. Okay, so let's do this here. One thing is they have mentioned that these are the directions of adjacent cells. So let's just go ahead and write that down. Directions is equal to 1, comma 0, 0, comma 1, -1, comma 0, and 0, comma -1. Okay, that should be the 4 directions, right? So let's start with our BFS. So what would we do? We would start as long as the queue exists, right? So yeah, the queue, which is sources here. So while sources, I want to check where was that thief present, right? So that's going to be sources dot pop left. And then I want to check like my neighboring cells to update their safety score, right? So I will do for directions, we can have our new coordinates of the neighbor, which is going to be equal to r plus this and c plus dc. Okay. So now let's just do a check, because these values might go out of bounds. So we want to check that row and column are within bounds. So we can just do that like this, as less than rows, and 0 is less than column is less than columns. And we want to make sure that it's not visited already, right? Because then we don't want to update the score, because that's already the shortest distance to the nearest thief. So let's just check that. This should be equal to -1, meaning it's not visited. And if that's the case, then I can do grid of row comma column is equal to the safety that I currently have. So I think it would have been better if I wrote that here. So current safety would be equal to grid of r comma c. Okay, so whatever the current safety was, +1, because another layer from that. And then now this has been added to this layer. So I will add that so that we can keep on expanding. Sources dot append this new row and column. Okay, so by the end of this, I have all my safeness scores for every cell, considering all of these thieves. And now, as we mentioned, we do a binary search on the answer. Okay, and to do that binary search, I want to consider like a left and right value, right? So we will have our left and right, which is going to be 0 and 0. So I think it would have made sense if I had kind of updated this value here. So yeah, let's just kind of get that from here. So if r in range rows, for c in range columns, we can do right is maximum of right, comma grid of r comma c. So that will give us the maximum possible score that we can have, right? Okay. So, and then we want to kind of maximize our answer. So let's just keep it as -1, because obviously that's not possible. And then we do a basic binary search, right? So we have left and right values. Let's do while left is less than or equal to right. We have mid left plus right divided by 2. And then we're going to check if is valid path of this mid value, then answer will be equal to mid. And then I want to push it further to get a more, a bigger, larger value, right? So then I'm going to update left is equal to mid plus 1 and then check. But if it's not possible, then it's too large. So I have to do right is equal to mid minus 1. And after that, we would just return answer. But we have not written this function, right? As valid path has not been defined. That is what I'm going to do now. So I think I can just write it here. So is valid path, and whatever I had actually passed to it. So that was actually the value of like what minimum safeness I wanted. So we'll do minimum safeness. And okay, so there are a few things which are like a few checks we can do initially for this. So my goal is to start from here and I have to go here, right? So obviously if the starting safeness of this cell itself is smaller than my minimum safeness, then that minimum safeness is not really valid, right? Or if it's the same here. So I can just do that check initially without really having to consider a path at all. So let's check that if grid of 0, 0 is less than minimum safeness, or the grid of, rows minus 1, rows minus 1 and columns minus 1 is less than, why did that happen? Is less than minimum safeness, then I can just return false, because then obviously this safeness which I took was not the valid one, or else we can continue. So as I mentioned, when we want to check if that's a path, like if that is the minimum for a path, then we start from here. We will do a BFS considering all the valid cells that I can go to. So again, we need a Q, a DQ actually. Let's have a DQ. Let's start from our source, which was actually 0, 0. And then we can have a visited set here. And I always make this typo. Let's add our starting coordinate. All right, and from here, we'll just do our basic BFS. So while Q, our comma C is Q dot pop left. And finally, our goal is to actually reach the end, right? So I just want to do that check. So if R is equal to rows minus 1 and C is equal to columns minus 1, then I can return true because I know I'm able to reach there from this. Or else, yeah, we'll just continue in our directions from there. So again, for dr, dc and directions, we'll have our new coordinates of the neighbor is equal to r plus dr, c plus dc. Let's again do a validation check. 0 is less than or equal to row is less than rows, and 0 is less than or equal to column, which is less than columns. And we want to make sure that it's not visited already because we don't want to keep following the same path again. So in row, comma, column, not in visited. And we also want to make this important check if that's the minimum safeness, right? So and grid of row, comma, column is greater than or equal to our minimum safeness. Then we know that this is it's a valid step that I can take to make that the overall safeness factor. So let's just go ahead and add this to visited, and we'll do that row, comma, column And then what else do I do? Yeah, we will add this to our BFS queue. Row, column, and yeah. So if I do this whole thing and I'm still not able to return true, that it means I never reached the end, and that means this is not a possible value. So I would return false. And what would happen after I return false? So my binary search would like it would check here, which is false. So then I know that that value is it's actually too large. So I want to keep a smaller score, right? So I hope I haven't made any mistakes. We'll just, okay, let's just write the time complexity up here. So time is O of n square log n. And our space complexity was O of n square. Okay. Let's see. Let's hope I didn't make any typos. Oh, cool. Great. Yep. As you see, it does work. And yeah, so that's how you solve this problem. I hope you guys understood. I know it was a pretty long video, but yeah, this is very helpful because the problems which came after this, like yesterday and today, they're kind of related to the same concept. So yeah, anyway, happy coding, everyone.